So density is a very, very important word in all of science, not just meteorology. And last video we discussed that density can be calculated by figuring out the amount of stuff, that's your mass, and dividing it by the size of your space, that's the volume. Density is equal to mass divided by volume. And once you know that, now we can look at another law that's pretty important in the world of weather. I like to say P is related to rho times T. And those variables stand for important words. P in this case is air pressure. That's a physical property which we have yet to go over in this class. And on the other side of the relationship, the big capital T, that stands for temperature. That's a physical property which we have gone over. And then in between is that funny looking P. That's the Greek letter rho. That stands for density. So we've just discussed that physical property of the air. So we have pressure is related to the density of the air times its temperature. So we have three variables here. And in order to figure out what's going to happen to one of those variables in the future, one of the three has to stay fixed. Understand? We have three variables. If we want to know what one of those variables is doing, we have to fiddle with the second one and fix the third one. So when we're thinking about thought experiments here in weather, we think about a piece of air. Maybe you're picturing a piece of air inside a balloon. That's called a parcel. So let's imagine we have a parcel of air and we're going to keep temperature fixed. That's not going to move. If we take our parcel and increase the pressure, squeeze the balloon, then the molecules inside are going to get closer together. So if we keep T fixed, that means the density has to go up. Increasing the left side of that relationship must increase the right side of the relationship. Now let's keep the pressure exactly the same. We'll just have a balloon. We won't squeeze it. We won't stretch it. We're just going to change its temperature. If we take that parcel and increase its temperature, the right side of the relationship just got higher, so the other variable there must get smaller. The density has to go down. As we heat up the molecules, they're going to shake a lot more. That's going to increase the distance between them, and the same amount of molecules are now taking up a bigger space. They're farther apart. So an increase in temperature decreases the density. And likewise, if we lower the temperature, then the density is going to increase. Think about yourself. When you get cold, you tend to shrivel up like this, stand close to your neighbor to stay warm. Well, the molecules do the same thing. They get closer together as they get slower, and they're taking up less room. So if you lower the temperature, you're going to increase the density of an object. So this is important because warmer air then becomes not as dense. Therefore, if you remember from the last video, it wants to rise. Things with lower density tend to float. And on the other side, colder air becomes more dense, so it wants to sink. This is going to cause the air to move around. And we know what that's called. That's called convection. I can show that to you in one of my favorite little demonstrations. I just have a tube of water right here in a square tube. I'm going to take a little green food coloring and pop it right in the top. Okay, right there. Okay. Now I'm going to grab that side of the tube and watch what happens. This water is all the same temperature. My hand is hot, so that's making this side of the tube hot. Warm things want to rise, so this warm water will rise up, which will force my food coloring this direction to your right, and then down this side of the tube. And I'm going to get a motion in this tube that's convection. And look at that, it's actually happening. Now I can stop that from happening really fast by grabbing this side and letting go over here. Now this side will start to cool down. This side will start to warm up. Let's take a look at the food coloring in there. So this is now going to get warm. This water will start to rise, and then it will go this direction across the top, and you'll start to see the food coloring pretty soon start to move the water the other direction. It took a little bit, but it's starting to happen. Let's look real close at that side. See, you can see the food coloring going up right there. And there it is, sliding that direction down the tube. Okay, so this is one way that I can prove that warm fluids will rise and cold fluids would sink. All I changed here was the temperature. The water pressure is the same inside. I can only fiddle with one variable. In this case, it was the temperature. All right, come check this out. Here I have a lab set up where I'm heating some water, therefore I've got red food coloring, and I'm making some water cold, therefore blue food coloring. I've got my thermometer right in the middle, and I would prove to you that definitely this is your warm water right here on the heat plate. You can see that we're well over 100 degrees, well over 110. And we'll go ahead and prove that this is definitely colder right here. You can see our temperature is going to dip down below 50, maybe even 40 degrees or so. So there's lots of ice there. So I'm going to go ahead and move the thermometer and get it out of the way. And we'll go ahead and turn off our heater right there. And let's start by putting the food coloring here in the warm water. Look how quickly that spreads throughout the water. Remember, the warm water molecules are moving very, very rapidly, so it makes sense that it will take not that long a time for the red food coloring to move its way around. We'll make it a little bit darker there. Really want to be able to see that. Now let's take some blue food coloring and we'll put it here in the cold water. Notice it's going to take a little longer for that to spread itself around. It's kind of clumpy. Notice it's even moving right to the bottom because we have our cold ice on top. So your coldest water is on the top and it's instantly moving to the bottom in that little stream of food coloring. So right away you can see that convection is happening here. But that's okay. I'm going to go ahead and stir this up a little bit so that we can go ahead and get a nice uniform color. Okay, and we'll make sure that the same thing happens up here for my red. So now what I'm going to do is I'm going to take this straw right here and I'm going to put my thumb over top. And that's going to trap some of this water inside this straw for a reason we'll go over in a future class. So we'll go ahead and this will go in the warm water and I'll put my thumb on top. Take a look, it's trapped in there. You can see that there in this camera. Now I'm going to take this and put this in the cold water down a little farther, pop my thumb off and put it back on, pull it out. Check this out right here. Look at that. You've got the warm water trapped on top, the cold water trapped on the bottom, and it's not moving. Why would it move? Because the density, this is less dense and it wants to be on top. This is more dense and it wants to be on the bottom, so it's going to stay there. This is a real important characteristic of our atmosphere, that when we get the warm air above us, it just doesn't want to move. Now in time, the temperature will moderate and this straw will turn purple. But it's going to take quite a long time. This is something you can do on your own if you wish. Now I'm going to ask you a question and you're going to answer it in your reading check after this lesson. So I'm going to do the same thing, but I'm going to go the other direction. I'm going to start by putting my straw in the cold water, then going over to the warm water and putting that in second. What do you think is going to happen? Write your best guess in the reading check question and then move on to the next video.